Hello, BNG101 class. Welcome to the lecture for our flipped classroom activity on Friday. I am Professor Brigham. I will be delivering this lecture as well as the flipped classroom activity on biodesign. So first, let's start simple with a simple question, a simple but kind of philosophical question. What is engineering? Well, we can define this in a number of ways. First of all, we can say, what do engineers do? And then, what is the process of engineering overall? So engineers apply science and technology to develop solutions to practical problems. And these problems are solved for the betterment of humanity. So engineers are trying to make our lives better. Seems simple enough. Engineering as an activity. We don't necessarily need to be engineers to do engineering, per se. Engineering as an activity is an innovative and methodical application of scientific knowledge and technology to produce either a device, a system, a process, which is intended to satisfy human needs. So we are essentially applying all the stuff that you are learning right now, science, mathematics, as well as learning about the different technologies that are out there, so that you are getting ready to both be engineers and do engineering as an activity. So a while back, there was a survey done among leaders in industry where the question was asked. This is, again, another maybe deceptively simple question. What attributes should an engineer possess? And the following bulleted list here is what they came up with. So heading the list, of course, you would imagine, engineer has to have good problem-solving skills. So they must be able to identify and define a problem that needs to be solved, develop alternative design solutions for that problem, as well as to implement the solution that was finally selected in order to solve that problem there. Engineers must have effective communication skills. So engineers must be able to convey their ideas, effectively, both in written and oral form. So that should probably tell you that in your career as a bioengineer, you're not going to get away from public speaking, you're not going to get away from writing. You need to have effective communication skills, because otherwise, how are people going to know that your idea is the best? Unless you tell them in a way that they can understand. Highly ethical and professional behavior, this is very important. Engineers must be able to recognize and resolve ethical dilemmas and behave in a professional manner at all times and in all circumstances. This may go without saying, but it always bears repeating, I think. It's a helpful thing to know. Engineers should have an open mind and a positive attitude. So if we are to be successful in any walk of life, let alone engineering, but certainly in engineering, if engineers are going to be successful in solving problems, they must be both imaginative and optimistic. So I'm going to ask for this flipped classroom activity you to be imaginative and certainly a bit optimistic in order to do the assignment that we'll be working through on Friday. So it's going to involve a certain amount of imagination. So this is actually open mind, positive attitude is a very important thing indeed. Engineers should be proficient in math and science. You may think, obviously, that's why we're doing the curriculum we're doing here in bioengineering. And it's true, engineers must be adept in mathematical techniques, and they also must be knowledgeable about science. The burden is on bioengineers to have knowledge of a wide variety of science, especially biology, chemistry, physics, those types of things, because bioengineering is such a wide umbrella here. Engineers should have technical skills. That goes without saying and really does not need any more talk about that. Certainly we need the appropriate set of technical skills if we are to perform well as engineers. Engineers need a motivation to continue learning. Things change, technologies change, so engineers have to change with the times. And you need that motivation to continue learning about this stuff. So given that not only technology but also scientific knowledge are expanding at such a rapid rate these days, engineers must be willing and able actually to acquire new skills and knowledge in their areas of expertise. Engineers should have a knowledge of business strategies and management practices. This is something that I've noticed in conferences I've gone to that are engineering conferences and not basic science conferences, where there's a big component of that deals with business strategies. There's a big component on management practices. It's very important as an engineer. If you're an engineer, you're going to have a team working for you, and you've got to know how to manage that team, and you've got to be effective in delivering a strategy. Engineers obviously should have computer literacy, honestly, like we all should in this day and age. But engineers especially must be familiar with the latest computer technology if they're going to use it in effective ways to solve problems that affect humanity. And engineers should understand world affairs and cultures, because we are in a global society, whether you like it or not, and it is critical to understand cultural differences among groups if one is to work in harmony with others from around the world. And as an engineer, you will have clients, vendors, even co-workers that span the world, that are all over the world. So you need to understand where everyone is coming from. Okay, so let's talk a little bit about the engineering design process. So here is a chart, a diagram that I used back when I was a postdoc for a biofuels process design group. So essentially what you have in the outer track here are technical skills, knowledge, different scientific knowledge needed in order to design biofuels, design and process biofuels from a variety of carbon sources. The inner track is the important thing here. It's a simplified engineering design process. So you have manipulate, measure, mine and model, and make. So what does that even mean? Well, manipulate, you're manipulating the literature, the scientific literature, seeing what has been done to create certain kinds of molecules, in this case biofuels. And you are devising a process in which to do this stuff. And then you measure that process, you run that process and measure it, and you get some data. And with that data, you end up mining the data, modeling what you see, and seeing how you can do this more efficiently. So we have manipulate, measure, mine, and model, and then eventually we're making something, we're making a process. And when you make that process, you might need to go back to the manipulate and do it all over again to refine that process. And then the bullseye, of course, is the product that needs to be made. In this case, we're talking about microbial biofuels. Now, this chart is fairly simple and maybe doesn't cover every step of the way needed for true engineering design. So more complex, and if you look on the internet, you can find tons of these charts. More complex design process diagrams might be needed to really illustrate what's going on here. And the engineering design process, at least, in terms of if you pick up an engineering design textbook, you'll see, well, you start off with needs assessment. Well, what's the need? What's the problem, right? And that's step one here in this process. And then you formulate what the problem is based on that need assessment. So you have, you're researching criteria and constraints, and then you're brainstorming possible solutions that might work. And so that's steps 2 and 3 here are that problem formulation. After that, you've got abstraction and synthesis, and so you're selecting the best solution for your problem, and then maybe you start constructing the synthesis. You're constructing a prototype solution. You analyze the data that comes out of that prototype, And then with those data, maybe you can implement the solution. Maybe you go back to redesign and do all this over again to refine that. So this is a little more in detail engineering design process, and I think one that makes a little more sense in terms of engineering design processes that you'll be doing as bioengineers. Okay, so let's kind of go through the process step by step here. So we start off with needs assessment. So with needs assessment, what are we doing? We're assessing needs, obviously, but what does that mean? We establish a need for a solution. We identify the objective to be achieved by a solution. What is it going to do? We got to know that. We want to identify who will benefit from this solution. What group of people. If we're in biomedical engineering, what subsection of patients are going to benefit? How are they going to benefit? Is it going to cure their disease? Is it going to ease their quality of life? We need to have that in our head. And how do we know they're going to benefit? Have we come at it from every possible angle? These are things we have to at least think about. And you want to begin, in terms of need assessment, you want to begin with the end in mind. You want to know where you're going. And that's not to say you should have a solution at the very beginning. You want to know, if you want to help paralytic patients, let's say, you want to begin with the end in mind. Do you want to help them in their mobility? Do you want to help in their quality of life? Know where you want to end up. You basically say, I want to help patients in their quality of life. And then, that your needs assessment is almost complete. And you can go on to the problem formulation. So there's a lot involved in the problem formulation, of course. Does the real problem differ from the problem as initially perceived? Obviously we go through many iterations of the design process and things change. So we got to ask ourselves these questions along the way. Is the real problem different than what you thought it was? If it is, then ask yourself, in what way? What or who was the source of the original problem statement? Did you get it from data from a professional society? Did you get this from one patient complaining, or multiple patients in multiple hospitals? The question, did the source bias the statement in some way? And that's always possible. Whether intentional or unintentional, it doesn't matter. But did the source bias the statement in some way? You've got to ask yourself that. And if yes, is the statement incorrect? Is it incomplete? And in what way? All these are important things to know. So then you want to structure a search for a solution. So identify as many different pathways leading to possible solutions as you possibly can. Write them down, make lists. I love to make lists. And then know where you're going, and direct your search a bit. You can direct your search by what we call pruning the paths, getting rid of the paths that probably won't lead to a satisfactory solution. Then you want to acquire and apply technical knowledge as appropriate when you're formulating your solution. You're formulating your problem and your solution. So in order to formulate your problem correctly and completely, and structure that search for a solution, you must make informed, i.e. knowledgeable, decisions on things. Identify the design specifications. If you have explicit and implicit constraints or boundaries, you might have the boundary that your solution shouldn't be super expensive. So you're going to work within those constraints and boundaries. Okay. And there's more. You want to identify the resources you're going to need, things like time, money, personnel, and things like that. And prioritize your design goals so you can effectively carry this out. So you want to continually review your lists, and you want to modify as needed during the remainder of the design process. So the theme here with engineering design is that you're making a list and checking it over and over and over and culling the herd, so to speak, to streamline an eventual solution here. And this is something that all engineers do when they're designing products or processes. And so for design goals, you want to be aware that your initial prioritization may be incorrect. Accept the fact that you might have done something wrong. You want to be open to change in your goal list. You want to focus primarily on the goals that are deemed most important. And, like with the flipped class activity, you're going to be working in teams where you might have come to a consensus as to what is most important and what is less of a priority. But recognize that all goals should be achieved by a final solution, however you do it. Okay, so once you have formulated your problem sufficiently, it's time to move on to abstraction and synthesis. So you're developing general concepts, abstract concepts, or approaches through which the problem could be solved. And then you want to generate detailed alternative solutions or designs for your problem. So first, solve problems that are similar, or experiences that are similar to the problem you're trying to solve. Expand your thinking, and again, for this flipped classroom activity, I'm going to be asking you to expand your thinking to what is possible and what is not possible. Obviously, you don't want your solution to contain any of the stuff that is not possible, but expand your thinking to include the entire realm of the possible. Use your imagination on that, and this is going to be important for the flipped class activity on Friday. You want to seek to develop solutions that are fully acceptable to all involved, to those that have to make your solution, to those that have to use it, acceptable to everybody. What approaches can be taken to solve the problem? Which of these approaches is most valid, and why? These are questions you have to keep in mind. Again, reconsider the problem statement. You've gotten this far. Is the problem statement still valid, or do we have to modify it in some way? And be creative. Again, another important thing for the flipped class. Be creative when you're thinking about alternative solutions. Combine each idea for achieving individual design goals into a solution or solutions. So seek to make the whole greater than the sum of its parts. Abstraction and synthesis continued. There's more. Again, expand your thinking. We're not done. We're not going to turn our brains off yet. Expand your thinking and be adaptable when you're considering how to eventually synthesize a possible solution to your problem. And then again, reconsider the problem statement. Is it still valid? Just keep asking yourself that question at every step. Must your problem statement be modified? And if so, then take steps to do that. And it's important to make the whole greater than the sum of the parts. Now, I have pictures of the 2016 Villanova Wildcat NCAA National Championship basketball team here for a reason. This team was the epitome of the whole being greater than the sum of the parts. They're all fine players and wonderful basketball players, but they are great teammates. They make a great team, and they put it all together in 2016 to win it all. And if you're a college basketball fan, you'll notice that a lot of Duke University basketball teams are like this as well. The whole is greater than the sum of the parts. And you can achieve great things with that, as this hopefully evidences. Okay, so once you've gone over the abstraction and synthesis again and again and again, you are ready to do some analyzing of any data that you've been collecting. So, we've synthesized a solution. Let's analyze the data that we get from that solution and see, is this still a viable solution? So you want to compare and evaluate your alternative designs. So choose a basis for comparison, first of all. An objective evaluation of the criteria is essential. Be critical. Again, you always want to be critical of your own work. Don't be a negative Nelly, but approach everything with a bit of skepticism. It's a healthy way to do it. It's the way scientists do it, and it's the way engineers should do it. Be critical. Don't think you've created the magic bullet here. Consider that there may be flaws and try to find them if you can. If it's not possible, great, but just be on the alert. And you want to consider the requirements, like the fabrication requirements and the implementation requirements for each solution. So consider the requirements for making your solution, and consider what the requirements are for using it. So for example, you have raw materials and standard parts. If you've got what they call off-the-shelf components to be used, consider how many of those you need. Do you need manufacturing processes that shape raw materials into something special, into something that is not standard? And think about what the impacts your solution will have. Will it have impacts on the environment? Will it have impacts on society? You got to think of things like that. Production, distribution, operation, disposal, any of that stuff. Think about any impact that might have, and compare and contrast all the requirements for each design solution. Are they ethical? Are the solutions ethical? You ask yourself that question in concept as well as in operation. You want to eliminate any alternatives that do not satisfy critical design goals at this stage. So if you have unmet goals or unmet needs here, that's obviously not a viable alternative according to your engineering design process. So eliminate those. It'll make your life easier. You want to anticipate failure, always a good thing to anticipate it, and avoid failure by eliminating weaknesses in your designs. And again, that's why you work on an engineering team. So we can all spitball ideas, or what we call ideate, and try to make this thing as bulletproof as possible. Ask yourself the question, does each design alternative satisfy ergonomic requirements? If it doesn't, there's a high likelihood that your customer will not want to use it. So you need to ask yourself this question early on, before you construct prototypes. And you can construct prototypes of the most promising designs if possible, if you have the budget for that. And then after the prototypes, you select the best alternative among the remaining designs. Revise and refine that design as appropriate. And then you're ready for implementation, full production, after successfully fabricating, testing, and evaluating the design prototype. Distribute to user populations your new solution. And then, once that's on the market, you keep track of it, you obtain feedback from customers. Customers like that as much as you do. Obtain feedback for the next generation of design. And then if necessary, when you do the next generation of design, you go and do the engineering design process all over again. Okay, so essentially we are going to be doing a design-based activity in class on Friday. But you should know a couple of things. All this design process that I've been talking about for 20 minutes, the entire process takes time. It takes weeks, months, maybe even years to get something right. These products weren't created overnight. The products you use, the products you see in the hospitals, they weren't created overnight. We're going to try to do something in one class session. For this activity, we're just getting a taste of the design process. How to think like an engineer, how to think about what is possible, how to use your imagination, the imagination side of engineering, not the math side of engineering. So you'll use aspects of the design process in the flip class, but we're not going to go through the whole thing. We just don't have the time. So here's what the flip classroom activity is going to be. So we'll split into groups, and the group organization will be posted on my courses for you to see. So get in your groups, and then each group will be given background on a design of a biomedical device. It's not going to be very technical. It's going to kind of give you the overview of what is going on, what the problem is trying to solve, and what it does to solve the problem. There'll hopefully be some description. There'll hopefully be some pictures. There'll definitely be descriptions available on this device, and you can ask me questions about these devices, and I'll answer them as best I can. And so I can try to give you as much information as possible about what the thing is doing. Then you'll be asked to modify a part of the design in concept. Again, not technical, in concept. Change the process, change the user experience. Again, this is not something that's going to require calculations, but just think about how it can be changed. As long as it's within the realm of possibility, this should be a good exercise. It doesn't have to be, you absolutely know it's going to work. That's not what this activity is about. You'll get points for creativity here, and you can discuss in your groups how to make that change. And so we'll be using something called ideation cards, and here's a picture of them right here. The front looks like this. They come from this company called Trig. It's a design company, and they employ very talented people. And they have on the back here, they have different ways that you can alter your design of your product. So here's one here that says celebrity. The user/customer is rich, impatient, vain, and aloof. Alter the process to achieve the end result. And you can see upside down here they have an example of that. High-end nightclub staff are trained to fulfill VIP customers' every whim to retain them as patrons. So that's an example of how someone has altered a design of something to solve the problem, or to basically to satisfy a certain type of customer in this case. If we're talking about a medical device, maybe we're talking about offering platinum care, where a nurse will be on call to answer questions or come out and provide support for use of a medical device or something like that. That's not of this care that's not available for general customers. Say, I don't know, but things like that. Just use your imagination. Maybe that's not a good example, but use your imagination on it. Okay, so Friday's class, what to expect. So you want to come to class having watched this recorded lecture. Split yourselves up into your groups. Be ready to start. I'll hand out the assignment sheet. I will have everyone pick 3 ideation cards. You'll brainstorm ideas. Each ideation card, let me back up just a bit, will have some kind of design change that you're supposed to make on it. And so you will do them one at a time. You'll brainstorm the ideas with your team, write down answers. What alteration was the ideation card asking? And then I'll ask, the bottom line is you synthesize a design change. Again, in basic terms, not in technical terms, based on discussion with your team. And then you'll write that answer down on the worksheet. And note here, please note, there's no one right answer to this. There are going to be many, many right answers. And it's going to depend a lot on your groups, whether you can think outside the box, your creativity as a group. So don't be stuck on there's one right answer. There's more than one right answer. There's always more than one way to do things. And again, if you need reassurance or need questions answered, I will be floating around the room and available to answer questions about this. Okay, so some final thoughts of this, and again, I think I've said it a lot by now, but it bears repeating. Be creative. Be creative with your solutions. But while you're being creative, work within the realm of what's possible. But expand your mind to fill the entire range of what's possible. Then consult with your teammates, come to a team decision, and again, I will be roaming around the room, and I think Dr. Lee will probably also be roaming around the room on Friday if you have questions about this, and we'll help you out as best we can. All right, on that note, I will see you on Friday. Thank you very much.